Let's talk about vector valued functions. Suppose I have a curve that is defined by r of t is broken into its components of f in the x direction and g in the y direction. Then we can write r of t as f of t, g of t. And of course we can extend this into the xy plane or to the z plane. So you can see sometimes this is a much easier shorthand way to write vectors. Now when we talk about the limits of a vector valued function, if we're trying to take the limit of the entire vector, then we can take the limit as t approaches a of f and the limit as t approaches a of g. If both of these limits exist, then that is the limit of r. Also, if we're looking for continuity of r, we say that r is continuous at a point given by t equals a if the limit as t approaches a of r is equal to r of a. Of course, the limit has to exist. And we're going to say that the entire function is continuous on an interval if it's continuous at every point. So we're defining things pretty much the same way as we defined them back in chapter 1. Now let's look at this curve right here. R of t is equal to t in the I direction plus aj plus a squared minus t squared in the k direction. And a is just some constant. So let's look at the continuity of the vector at t equals 0. Does the limit exist? So the limit as t approaches 0 of r of t is the limit as t approaches 0 of ti plus the limit as t approaches 0 of aj plus the limit as t approaches 0 of a squared minus t squared in the k direction. All right, so this is 0 in the I direction, so a lot of times we'll leave that off, plus a squared k. Now, the limit exists. What is r of 0? Well, that's 0i plus aj plus a squared k. Since r of 0 exists, and the limit as t approaches 0 of r of t equals r of 0, those are the same, then we say that the function is continuous.